video, we'll be looking at calculating the regression line for a positive relationship. All right, first off, the formula for a regression line we'll see is y prime equals a plus b times x. All right, in this formula, y prime is the calculated value for y. So this is the value we calculate for the dependent variable. In order to find that, we take a, that we have a formula for here, plus b, which we also have a formula for here, times x. So x in this case would be the value of the independent variable that we want to make a prediction for. All right, so similar to what we did with correlation, we're going to go to an example. Okay, for example 1, where we had the number of children versus the number of siblings for a woman, we want to try to predict the number of children for a woman with 7 siblings. All right, to do that, we would go back to that same table that had 5 columns in it, the x, y, x times y, x squared, y squared columns, and we're going to pull our numbers from there. So a equals, in the numerator, sigma y, bottom of column 2. Sigma x squared, square inside, bottom of column 4. Sigma x, bottom of column 1. Sigma xy, bottom of column 3. In the denominator, we have n, 6. Sigma x squared with the square inside, so that's the bottom of column 4 again. And then sigma x squared with the square outside, bottom of column 1, squared. So do the multiplication in the 2 terms in the numerator, do the multiplication and the squaring in the 2 terms of the denominator, do the subtraction in both cases, and when I'm all done, I have a equals 0.833. All right, now, unlike the R value, here we do not have a built-in range. These A and B's could literally be anything. But we'll see at the end a simple way to sanity check this number and see if it's rational. All right, now, when we get to B, you've got more of the notation. But the good news on B is we've already calculated both the numerator and the denominator. If you take a look at the denominator, it's exactly the same as the denominator of A. And you'll see here we have 60 carried down there. So that's one thing. The numerator of B is the same as the numerator of R. So if we go grab that 90 out of there, you could bypass all the math here. So in any case, you end up here with 90 over 60, do the division, you end up with a B equals 1.5. Now, once you've calculated A and B, you have y prime equals 0.833 plus 1.5x. Now, as I mentioned, you can't put boundaries around what value A can be, what value B can be like you did with R. But I said we could sanity check it. Now, first thing, if you want to sanity check it, once you have this formula, put a 0 in for x. Okay, so let's try to predict the number of children for a woman who has no brothers and sisters. 1.5 times 0 goes to 0, so we're left with 0.833. So this model would predict 0.833 children for a woman with no brothers and sisters. And if we go back to the graph, and I apologize for having to scroll through here, 0.833 would look to be a valid place for that. So from a sanity check standpoint, that looks pretty good. The second thing we can do then is we look at B. B is basically how fast the line changes. So when we look at B for 1.5, what that is saying is for every brother and sister that the woman had in this data, it looks like it added 1.5 children. And if you go back again and look at that graph, as you go over to the right one, you go up 1.5. Go over to the right another one, go up another 1.5. And that looks pretty legitimate. So that does look like a fair statement. And so, like I said, you can't absolutely check these, but you can kind of sanity check them. So once you've done that, say, all right, yeah, this looks like a legitimate regression line for this. We want to predict how many children a woman with 7 brothers and sisters would have. So we plug a 7 in for x. 7 times 1.5 is 10.5, plus 0.833 is 11.33. So we would predict 11. Now, just one caution here before we go here is be very careful as you get to the outer edges of where you have X values. Make sure you check out the book where it talks about extrapolation. You want to be very careful with extrapolation.